Hey guys, so today we're going to be covering another math concept which is commonly known as Simon's favorite factoring trick. So just a short summary, this is a trick that's seen very often on competitions such as the AMC and Amy. So I thought it would be useful to cover this. So what is Simon's favorite factoring trick? Well, it's kind of a method that's used to factor Diophantine equations, such as this one right here. We have mn minus 3n plus 4m equals 13, where m and n are both integers. So essentially we have the product of two linear terms, m and n, and the addition or subtraction of either of those terms individually. And then that entire thing equals a constant, which is, in this case, 13. So just looking at it, there doesn't really seem like an easy way to do it besides bashing. But what we can try to do is try to factor it. So if we're going to factor it, our end expression is going to look something like this. We have two parentheses and m and n as two of the factors, or in the two factors, because we want an m times n term, so that's where we're going to get that. We want negative 3n, so let's put a negative 3 here, because when we FOIL it, we're going to get negative 3 times n. And we want 4m, so let's put a plus 4 here as well. So if we expand this, mn plus 4m minus 3n, we're going to get a negative 12 at the end. And that's not exactly the original expression. So what we can do is actually subtract negative 12 from 13 and get 1. And if you move negative 12 to the other side, you'll see that it's the original expression. So we can say that this right here is equal to 1. Okay, I'll just rewrite it over here for more space. M minus 3n plus 4 equals 1. So if we know that m and n are both integers, what does that mean about m minus 3 and n plus 4? That means that both of these are also integers, and if they multiply to 1, they must both be factors of 1. And the factors of 1 are, just only 1. So we can either have 1 and 1, or m minus 3 equals 1, n plus 4 equals 1. We could also have negative 1 times negative 1, because two negatives, when you multiply two negatives, you get a positive. Yeah, and just make sure that you remember the negative case, because a lot of time people forget about this case and they miss the answer by maybe like a few solutions. Okay, so in this first case, we have m minus 3 equals 1, n plus 4 equals 1. If m minus 3 is 1, m is 4. If n plus 4 is 1, n is negative 3. So if we plug it into the original equation just to check if it works, we get 4 times negative 3 is negative 12, minus 3 times negative 3 is plus 9, plus 4 times 4 is 16, which is going to be negative 3 plus 16, which is 13. And that works. So this is one possible solution. Now we have this other case. If m minus 3 is negative 1, m is 2. And if n plus 4 is negative 1, n is negative 5. And you can check if this works on your own. I'm going to just assume it works for time's sake. So these are our two solutions. Okay, I have a second example just to show you a different case. We have 2mn minus 5n plus 2n is 13, and again, m and n are both integers. Okay, so this is a bit different because now we have a coefficient of 2 on the product term. So let's see what happens if we try to multiply, or try to factor it, sorry. We'll have, let's say, 2m times n, because we want to get the 2mn term. We can have a plus 2 here, because we want to get the 2n. But here's the problem. We have to get a negative 5m, but our coefficient on the m term is 2. So that's not really going to work, because if we have 2 times m, that's always going to be even, and 5 is odd, so that's not going to work. So something we can do is we can multiply this original equation by 2. So what we're going to get is 4mn minus 10m plus 4n equals 26. And let's see what happens if we try to factor it now. We get 2m, 2n, we want 4n, so we have plus 2 again, and now it works. We have a negative 10m, so we have a negative 5 here. Okay, now what happens if we expand this? We have 4mn minus 10m plus 4n. Well, we have a negative 10 now, and that's not what we want. So we can go to the original equation and subtract 10 from this side, and that will be 16. So this will be 16. Okay. So now we have the expression 2m plus 2 times 2n minus 5 is equal to 16. Notice that we can divide this term by 2, so we actually get m plus 1, and or this one stays the same, so this is equal to 8. So I factored out a 2 out of this first factor here, and then I divided 16 by 2. Okay, and also notice that 2n minus 5 is always going to be odd, because an even minus an odd is always odd. So when we consider the factors of 8, which are 1, 2, 4, and 8, as well as the negative counterparts, we cannot have 2n minus 5 equal an even number. So the only possibilities that actually work are when 2n minus 5 is 1 and n plus 1 is 8, or 2n minus 5 is negative 1 and n plus 1 is negative 8. So again, we're going to have two solutions. In the first one, we have n plus 1 is 8, so m is 7. 2n minus 5 is 1, so n is 3. n plus 1 is negative 8. This gives us m equals negative 9. And 2n minus 5 is negative 1, n is equal to 2. And you can check these on your own again. These are two solutions. Okay. Now, as always, I've also brought a AMC problem for us to try. You can just ignore the top, that was a failed recording. So this is the AMC 10B 2021 problem number 11. It says, Grandma has just finished baking a large rectangular pan of brownies. She's planning to make rectangular pieces of equal size and shape with straight cuts parallel to the sides of the pan. Each cut must be made entirely across the pan. Grandma wants to make the same number of interior pieces as pieces along the perimeter. What is the greatest number of brownies she can produce? Okay, so what this problem is essentially saying is we have a pan like this. Let's say the length is A, the width is B. We're going to make a ton of cuts like this, parallel to the sides. And then we want the number of interior brownies to be equal to the ones on the outside. Okay, so if you're not sure what to do, just assign some variables. So let's say the length is a and the width is b. What we want to make the interior brownies equal to the brownies on the outside. So how many brownies are in the interior? Well, if we take away one on each side, the interior is going to have a length of a minus 2, because you can think about it like we're taking away one brownie on each side, and if the original length was a, now we're going to have a minus 2, and similarly we can have b minus 2 for the width of the interior rectangle. Yeah, sorry, the drawing's a bit messy, but I hope you get the idea. So the number of interior brownies is going to be a minus 2 times b minus 2. And the number of exterior brownies, well, if we add 2a and 2b, just adding the top rows and the bottom rows and each of the two columns, it's actually going to overcount each of these 4 corners. Because when we count this row here, we're going to count the square ones, but when we count this column here, we're also going to count this square again. So we have to subtract each of those once, and that's going to be 4 because we have 4 corners. Okay, now we have an equation like this, and what do we want to do to find the answer? We want to find the greatest possible number of brownies that grandma can produce, and that's going to be the same as saying maximize a times b. Okay, now let's just simplify this equation. We have ab minus 2a minus 2b plus 4 equals 2a plus 2b minus 4. And this is the same as ab minus 4a minus 4b plus 8 equals 0. So we can move that to the other side, say minus 8. And now, what have we been doing this entire time? Well, this is the same as the other examples, so we can use Simon's favorite factoring trick. We can write this as a minus 4 times b minus 4. We're going to get the same 3 terms, except we have a plus 16 because negative 4 times negative 4 is 16. So we have to add 16 to this side, and that's going to give us 8. And now it's just a matter of checking each of the possible cases. And notice that in this case, a and b can't be negative because, I mean, you can't really have negative lengths of brownies. So let's just try all the positive factors. We have 1, 8, 2, 4, 4, 2, and 8, 1. Okay, my pen's running out of ink. Notice that a and b are actually symmetric, so we don't have to check 2 of these cases because they're already checked in the first 2. Okay, so now we have 2 cases. A minus 4 is 1, b minus 4 is 8, so this gives us a equals 5, b equals 12. Or we can have a minus 4 is 2, so a is 6, and b minus 4 is 4, so b is 8. And, sorry, we want to maximize a times b. So a times b in this case is 48, a times b in this case is 60, so we want this case here. And so the answer is going to be just 5 times 12 is 60, and that's going to be answer choice D. Okay, so that's all I have for you today. Be sure to like, comment, subscribe, and let me know what other concepts or problems you want me to cover next. Bye.